Grass waterways. Grass waterways are channels used for conveying water safely at some outlet point. Suitable vegetation is allowed to grow in this type of waterway. The objective of waterways within a conservation system is to transport this runoff at non-erosive speeds to an appropriate outlet point. Our goal here is to reduce the speed of the flowing water so that it becomes non-erosive. So it requires meticulous design so that dimensions are adequate. It should be able to handle peak runoff event which occurs once in 10 years. So an extreme event may occur once in 10 years in a certain area, and your waterway should be able to handle that extreme runoff event. So mainly there are three types: diversion channels, terrace channels and grass waterways. In this chapter we will be learning in detail about grass waterways. What are grass waterways? They are channels, either natural or man-made, designed to transport concentrated flow at safe velocities from catchment areas. It is used for disposing excess water from terraced croplands, bunds and ponds. It is used in agriculture to dispose excess water. It is carefully sloped and the design is also meticulously done so that it can handle the peak runoff events. So you may commonly find that grass waterways may be trapezoidal, parabolic or triangular. Most natural grass waterways will look similar to a parabolic shape. Man-made channels may be trapezoidal, triangular or even parabolic shape also. Design includes depth, width, velocity and discharge. So we need information about climate of that region. We need the data on rainfall. You may use certain appropriate models to convert that rainfall into runoff. Based on that, you will design the depth of the waterway, width of the waterway, and you should be able to estimate the velocity and discharge also. The volume of water this waterway can handle per unit time. So waterways are used for carrying the excess water from bunds. So from bunds, this excess water is diverted towards this grass waterway, and this grass waterway will again divert it to some suitable point. Now in this dam, the overflowing water will start getting diverted towards this grass waterway. This is an emergency spillway. So emergency spillway is in form of a grass waterway, so that the speed of water is reduced and it becomes non-erosive. Excess water from pond can also be diverted into some grass waterway and safely disposed. Commonly you will find these three shapes: trapezoidal, parabolic and triangular. Trapezoidal grass waterway, this offers good stability. It also reduces risk of erosion and also reduces risk of channel instability. So these offer very good stability. Then parabolic grass waterways. These shapes mimic natural water flow. It facilitates efficient sediment transport without causing any excessive deposition. And then there is triangular grass waterway, which is suitable for steeper slopes. The capacity is little less than the other shapes, but it is suitable for steeper slopes. So it may have reduced flow capacity compared to more complex designs. Now this is a trapezoidal shaped grass waterway. To compute the area of this trapezoidal grass waterway, we can use this formula: A is equal to BD plus ZD square, where B is the bottom width, D is the depth, Z is the side slope, and these I have already described, it is the depth. So top width is nowhere to be seen in this equation. A is equal to BD plus ZD square. To calculate the wetted perimeter, we'll be using this equation: B, that is the bottom width, plus 2 times the depth multiplied by square root of side slope square plus 1. If we substitute these values, we can calculate the wetted perimeter. Hydraulic radius is the ratio of area to perimeter. R is equal to A divided by P. So the equation is BD plus ZD square divided by B plus 2D root Z square plus 1, and top width is B plus 2DZ. So if these values are provided, you can calculate the area, perimeter, radius, and from this we can also estimate the velocity using the Manning's equation. Okay, so we'll discuss this after discussing some other shapes. Let us discuss the parabolic shape now. Parabolic shaped grass waterway. Now, to calculate the cross-sectional area of this parabolic shaped grass waterway, we need the top width and the depth. Okay, so A is equal to 2 by 3 multiplied by top width multiplied by depth. Wetted perimeter is T plus 8D square by 3T. Again, depth and top width are required to calculate the wetted perimeter. Hydraulic radius then can be easily calculated as it is the ratio of area and perimeter. So R is equal to A divided by P. Top width can be calculated using this equation. T is equal to A divided by 0.67D. So it is quite simple for triangular shaped grass waterway. A is equal to Z D square, where Z is the side slope, D is the depth. Wetted perimeter is 2D root Z square plus 1. Hydraulic radius is the ratio of area to perimeter, A divided by P, and top width can be calculated using this equation. T is equal to 2dz. So let us discuss the recommended velocities in grass waterways. 1 to 1.5 meter per second is considered to be safe for most well-established grass waterways with good ground cover. So this velocity 1 to 1.5 meter per second will minimize the erosion risk while still allowing efficient water flow. If velocity is increased, okay, if the flowing water is having velocity ranging from 1.5 to 1.8, then it is pushing the boundaries. Okay, it is still considered as acceptable, but for only those waterways with excellent grass cover and robust erosion resistance. But you will rarely find a grass waterway having excellent grass cover. Now, if the flowing water has velocity in the range of 2 to 2.5 meters per second, then it may be very risky. It may become erosive. So, velocities which are more than 2 meters per second should only be allowed in exceptional circumstances. Okay, if there is exceptional grass cover and specific design elements such as check dams, which will help in breaking up the flow and thereby preventing erosion. Otherwise, these velocities may not be accepted. Okay, so 1 to 1.5 safest, 1.5 to 1.8 acceptable. Little more than this may not be totally safe. But if there are check dams on the way, then it will help in reducing the velocity and preventing erosion to a certain extent. These are some of the suggested maximum velocities of surface water flow on soils with different textures. So for sandy soils having bare to light grass cover, 0.4 meter per second is considered as the maximum safe velocity. Beyond that, erosion will start occurring. But if the soil texture is sandy and the grass cover is very good, then up to 1.2 meter per second is considered to be safe. This is the maximum velocity. Beyond 1.2, even though the grass cover is very good, the runoff will start becoming erosive. So soil particles will start flowing with the runoff. Okay. So then we have sandy loam, 0.6, 1.2 and 1.5. These are the maximum velocities for bare to light grass cover, medium grass cover and very good grass cover respectively. And if the soil texture is medium to heavy clay and if it is having very good grass cover, okay, then 2 meters per second can also be allowed. This is the maximum range. Beyond this, it will become erosive. Okay. And if the soil is clay soil, but the grass cover is light, then only 1.2 meter per second is the maximum recommended velocity. Beyond this, the velocity will become erosive. So it should not exceed this value. So before designing, you must consider these points. Estimate the velocity. If it is beyond this value, then redesign. Okay. You may change the depth, you may change the dimensions, you may reduce the slope in order to reduce the velocity of water flowing in this type of waterway. So design of grassed waterway includes consideration of peak runoff. The highest runoff, which may occur once in 10 years. It is the expected runoff over a period of 10 years. Then we need some reliable models which can estimate the peak runoff. We need stability after the installation, so such measures are also to be considered. Then flow velocity concept will also be considered in the design of grassed waterway. So how will you estimate the peak runoff? The peak runoff can be estimated from standard methods such as rational method, hydrograph method, SCS method and other methods. Post installation stability. So design considerations are based on conditions which are expected 2 years after installation. So it allows for establishment of stable grass vegetation lining so that erosion can be prevented. So design also relies on concept of maximum allowable flow velocity in the channel. We had just discussed that, with a focus on peak flows not exceeding the permitted values. For example, in clay soil, we may not allow the velocity to increase beyond 1.2 meters per second. Okay, so we may change other dimensions so that velocity is within that permitted range. So all these data are required. Some models you may have to use to estimate the runoff, and post installation stability is also considered in the design of grassed waterway. So for designing a grassed waterway, usually a trial procedure is adopted. You may have to calculate the area, then you will have to calculate the wetted perimeter. From area and wetted perimeter, you will be calculating the hydraulic radius, then slope you will assume, okay, and then you will estimate the velocity using this Manning's formula. In this Manning's formula, V is the velocity of flow in meters per second, S is the slope of that waterway, R is the hydraulic mean radius of the section, that is the hydraulic radius. It is A divided by P, and N is the Manning's roughness coefficient. So velocity and Manning's roughness coefficient are inversely proportional. Higher the roughness, lower will be the velocity in the waterway. Higher the slope, higher will be the velocity, because they are directly proportional. So from the table you can get the appropriate values of roughness coefficient suggested by Manning. So these are some of the roughness coefficient values. For bare soil, the N value is 0.02 to 0.045. For sandy soil, you can see it is 0.03 to 0.045. For soils which are having stony surface, okay, the roughness is slightly increasing, 0.035 to 0.045. Okay. So for grass waterways, you can see that roughness is more depending on the vegetation also. Okay, so if the grass cover is very good or excellent, okay, so N value may go up to 0.08 or beyond that. So roughness represents the resistance to flow offered by the channel bed and the banks. It is influenced by the type and condition of the channel materials, vegetation and roughness. So these values have been determined experimentally and they will vary from channel to channel. However, depending on the type of channel that you have constructed, you can pick the n values from this table. Now let us solve one example of trapezoidal grass waterway design to understand the procedure. Now there is a grass waterway which is to be constructed with a bed slope of 0.4%. Okay, so bed slope is just 0.4%. Side slope is 2 to 1. This is 2 horizontal to 1 vertical. Okay, so these are the side slopes. Find the bottom width of the trapezoidal grass waterway, which is required to carry discharge of 5 meter cube per second at a depth of 1 meter. Manning's roughness coefficient is 0.06. So this channel should be able to carry 5 cubic meters of water per second. Okay, when the depth of water is 1 meter. So let us find the bottom width, which will allow this channel to carry the required discharge. So roughness is given to us, even the discharge value is available, depth D is 1 meter, Z side slope is 2 by 1, slope of the channel is 0.4%. So let us substitute these values into the equation. Assume a bottom width. So let us start with trial and error. Let us assume a bottom width and calculate the area of a trapezoidal grass waterway. So we'll be using this equation A equal to BD plus ZD square. Once we get the value of area, we can compute the velocity of flow using this equation, V equal to Q divided by A. Once velocity is obtained, you can compare it with the velocity estimated using the Manning's equation. Okay, so first you will calculate the velocity using this equation, Q, which is given to us 5 meter cube, and area whatever we get we will substitute, we'll get some velocity. We'll compare this velocity with the velocity that will be obtained from Manning's equation, V equal to 1 by n r raised to 2 by 3 s raised to 1 by 2. So if they are not similar, we will change the value of bottom width and perform these steps again. Okay, so let us solve. So first let us start with bottom width value of 3 meters. So bottom width is 3 meters. Let us substitute depth already given to us 1 meter. A equal to BD plus ZD square. On substituting the values of B and D, I am getting area as 5 meter square. Now substitute this in the velocity equation. Q equal to AV, therefore V will be equal to Q by A. So V is equal to 5 meter square divided by, Q is 5 meter cube divided by area, which is 5 meter square. Very convenient. So 5 by 5 is 1. So velocity is just 1 meter per second. It seems to be safe velocity, but steps are still remaining. Let us now compute the velocity using Manning's equation. V equal to 1 by n r raised to 2 by 3 s raised to 1 by 2. So first we need to calculate r. So we need wetted perimeter. P equal to b plus 2d root z square plus 1. Let us substitute the value. B is equal to 3 plus 2 multiplied by depth, which is 1, multiplied by square root. Z side slope is given to us 2 to 1, so 2 square plus 1. I am getting wetted perimeter as 7.47 meters. Hydraulic radius is A divided by P, which is 5 by 7.47, which is equal to 0.67. So hydraulic radius also we have obtained. Now let us substitute this in Manning's equation. V equal to 1 by n r raised to 2 by 3 s raised to 1 by 2. We will get velocity equal to 0.806 meters per second. They seem to be different. This is 1, this is 0.8. So now what we will do, we will again assume another value of bottom width. velocities are different. Let us assume another value and again redo this, again do this steps. Okay. Now let the bottom width be 4 meters. Now doing the same steps, A equal to BD plus ZD square gives us 6 meters square. Velocity V equal to Q divided by A, that is 5 divided by 6. Now velocity is 0.833 meters per second. It is safe. Now let us again calculate the wetted perimeter, then the hydraulic radius, so that we can substitute it in the Manning's equation. Upon substituting these values in the Manning's equation, we are getting the value of velocity equal to 0.837 meters per second, which seems to be quite close. Okay, 0.833 is 0.837. So this is sufficient. We can further refine it, but no need to do it. Bottom width of 4 meters seems to be appropriate. It can handle discharge of 5 meter cube per second. So this is our answer. B is equal to 4 meter because the velocities obtained by Q by A and Manning's equation are similar. Now let us design a parabolic grassed waterway. In this waterway, we have to calculate the discharge. Okay, discharge is area multiplied by velocity. Compute the discharge in this parabolic grassed waterway having top width of 1.3 meters. Water is flowing at a depth of 40 centimeters, which is 0.4 meters. Manning's roughness is given to us. N is equal to 0.04. Slope is 2%. And Manning's roughness coefficient, again I have already discussed that, 0.04. Now let us substitute the values to get the cross sectional area. A is equal to 2 by 3 multiplied by top width multiplied by depth. Is the top width provided? Yes, it is 1.3 meters. What is the depth? It is 0.4 meters. So I will get some value. Again I will calculate the wetted perimeter, which is T plus 8D square by 3T. I'll substitute the values. I'll get some answer. Now hydraulic radius is very easy to calculate. A divided by P. Once I obtain R, it will be substituted in the Manning's equation to get the estimate of velocity. This velocity is multiplied by the cross-sectional area to get the discharge. Q is equal to A multiplied by V. So these are the steps with the values. A is equal to 2 by 3 TD, T is 1.3, D is 0.4, the area is 0.35 meters square. Wetted perimeter T plus 8D square by 3T. Upon substituting the values, the wetted perimeter is equal to 1.628 meters. Now ratio of A to P will give me hydraulic radius R. R is equal to A divided by P. Therefore 0.35 divided by 1.628 will give me 0.215 meters. This is the hydraulic radius. Now let me substitute hydraulic radius in the Manning's equation. V is equal to 1 by N R raised to 2 by 3 multiplied by S raised to 1 by 2. Upon substituting these values, I will get V as 1.268 meters per second. We are supposed to calculate the discharge. Okay. Because we have area and velocity, it's very easy to calculate now. Discharge is equal to area multiplied by velocity. Area is 0.35 meters square, cross-sectional area, and velocity is 1.268 as estimated by Manning's equation. So discharge is estimated to be equal to 0.44 meter cube per second. So if there is a parabolic channel having top width of 1.3 meters and depth of flowing water is 40 centimeter, then the discharge it can handle is 0.44 meter cube per second. Okay, so this is the discharge in this parabolic grassed waterway. Let us solve one more problem related to the design of parabolic grassed waterway. Now design a parabolic grassed waterway to convey a peak flow of 6 meter cube per second on a 1% slope over an erodible sandy soil with Bermuda grass vegetation in a good stand cut to a height of 60 millimeter. So peak flow is given to us. It should be able to convey this 6 meter cube per second. Slope is also provided, 1% slope over an erodible sandy soil which is covered with Bermuda grass vegetation cut to a height of 60 millimeter. Okay. Maximum permissible velocity according to the proposed vegetation cover and local soil is 1.5 meters per second. So 1.5 meters per second is our maximum permissible velocity in this parabolic grass waterway. Now let us design. Now discharge is given to us. Slope is also provided 1% which is equal to 0.01. Permissible velocity is 1.5 meters per second. Roughness however is not provided here. Okay, so we'll be using some other equations here. Select a suitable value according to the vegetation retardance class CL. Okay, so this CL can be estimated knowing the length of plant stems and the density of stems per unit area. So we will get value of vegetation retardance class instead of N. Okay, and it is estimated if you know the length of the stems and density of stems per unit area. So let us design. Now stem height is 0.06 meters. Yes, it is given to us 60 millimeters which is equal to 0.06 meters. Density of stems per unit area is provided, it is equal to 5380 stems per meter square. This may be the typical value in that area. Okay, per meter square how many stems? 5380. Okay, now retardance class, vegetation retardance class CL can be estimated using this equation. CL is equal to 2.5 m multiplied by root of m. Okay, here small m is the stem height and capital M is the density of stems per unit area. We have both the values. M multiplied by root m raised to 1 by 3. So let us substitute the values. I will get the vegetation retardance class equal to 6.75. Now the roughness can be estimated from this CL value. There is a relation between N, roughness, and vegetation retardance class CL. So N is equal to exponential 0.126 multiplied by CL minus 4.16. So our answer will be 0.036. N is equal to 0.036 upon substituting the value of retardant class 6.75 into this equation of N. So once N is obtained, we can now design, calculate the hydraulic radius. Now Manning's equation is V equal to 1 by N R raised to 2 by 3 multiplied by S raised to 1 by 2. Therefore R raised to 2 by 3 will be equal to Vn divided by S raised to 1 by 2. Now what we may do, this 2 by 3 will go on the other side. It will become Vn by S raised to 1 by 2 raised to 3 by 2. Do we have the value of velocity? Yes, if velocity is 1.5 meters per second and we just calculated, it is equal to 0.036, slope 0.01, 1% already provided in the problem, and raised to 3 by 2 which is 1.5. So on substituting these values, we will obtain the value of R which is now equal to 0.396 meters. This is the hydraulic radius. R is 0.396 meters. Now we will calculate the area of the channel. Okay. Q, is it provided? Yes, in the statement of the problem itself it is provided. Should be able to handle peak flow of or discharge of 6 meter cube per second. So Q is 6, velocity 1.5. So I will get the cross sectional area, which is 4 meter square. Now let us calculate the design depth for the parabolic section. So D is equal to 3 by 2 multiplied by R. Okay, you can use this equation to calculate the depth for this parabolic section. So 3 by 2 of R. What is the hydraulic radius? It is 0.396. So 3 by 2, which is 1.5 multiplied by 0.396 will give us the depth. It is 0.594 meters. Top width, you can calculate A by 0.67 D. So 4 by 0.67 multiplied by 0.594, top width should be 10.05 meters. Okay, it's quite wide. Okay, because it should be able to handle discharge of 6 meter cube per second. So it's quite a wide parabolic section here. Top width is 10.05. Now check whether this capacity is adequate or not. Now Q is equal to AV, which is equal to 0.67 TD multiplied by V. Upon substituting value of top width, we just calculated 10.05. Velocity 1.5 already given. D we have calculated 0.594. Upon substituting these values here, we will get the answer for discharge. Discharge is 5.99, which is approximately equal to 6 meter cube per second. So our design is appropriate. Now we may add additional 20% freeboard to the design depth. So instead of 0.59, let us add 20% freeboard. So it will become